Okay, so hello everyone. In this video, we are going to cover Internet Protocol versions. So, in this video, we will discuss about IPv4, IPv6, and at last we will discuss need of IPv6. So, let's start with introduction to IPv4 header. So, today we are going to discuss the header of IPv4. What is the meaning of IPv4 here? It's an Internet working protocol that works at network layer. In today's time, we all are using the internet and various applications like email, WhatsApp, Facebook. What are we doing majorly with these applications? We are trying to share data, and that data travels in the form of packets. So what is the major force behind this? It's IPv4, which is an internet working protocol that works at the network layer. Before discussing the header, let me give you a small basic introduction. IPv4 is a connectionless protocol. Okay, if you have to send data from source to destination, you want to send packets, but you don't create any connection at first. What do you call this? Datagram service. Okay, we have discussed datagram service and virtual circuit switching before. So we are using here datagram service. Datagram service means I have a source and a destination. The source can be connected to the destination through different ways. By connectionless, we mean when the packet travels from source to destination, no connection will be created. What is the meaning of datagram? Any route can be followed. Okay, compared to this, the other concept is virtual circuit. In virtual circuit, what do? First, we create a connection. So, according to that connection, all packets are followed. But in datagram service, any packet can travel from anywhere. Obviously, the reliability is less here. What is the reason for this? It may be that some packets get missed on the way because all the packets reach through different routes. Okay, so obviously, no connection was made before, and making connections means to reserve something, reserving bandwidth, resources, or something like that. IPv4 does not do that. But if the upper layer, like the transport layer or particular application, says that I will transfer data only if there is a connection, then we will use TCP connections. But if we talk about IPv4 itself, it is connectionless and it is a datagram service. Okay, a packet can travel from anywhere and reach its destination. So this is IPv4. Now, what is the significance of the header here? What is the use? A data packet contains data, but if you want to post a letter to someone, you simply write a letter and give it to a courier or post office. Where will it go? It can't reach anywhere. It will remain there only. Why? Because we have not mentioned anything on it. What is my address? What is the destination address? Or where we want to send? Okay, how it will reach is the problem of post office, but you will have to add, at least mention the destination address. We call this envelope. On the envelope, we write all the things. That is what a header is. Okay, so the header tells how the packet will move, how it will travel, or what will its characteristics. Now we will discuss IPv4 header structure. Okay, in the IPv4 header, we have a total of 13 fields. Out of these, 12 fields are mandatory and its total size is 160 bits. What is the meaning of 160 bits? 20 bytes. This is mentioned in the header of IPv4. What should be its minimum size? It should be 20 bytes. Okay, and what is the maximum size? That is 60 bytes. The payload is the pure data that is coming from the upper layer. Which layer is above the network layer? The transport layer. Okay, what can be the size of data coming from the transport layer? Minimum 0 and means no data is coming, or maximum 65,515 bytes. If you add the minimum header of 20 bytes, the total becomes 65,535, which is the value of 2 raised to power 16. So the total length of the datagram can be 2 raised to power of 16. This whole packet we call datagram. Field by field explanation. First field is version. The first field is version, which is 4 bits. Its value is 0100 in binary, which converts to 4 in decimal. Okay, denoting IPv4. In IPv6, this value will change to 0110, meaning 6. This version field act like the engine of a train. The first part that shows what type of packet this is. This is version. Now, header length. The second field is header length. This is 4 bits, meaning it can have values from 000 to 1111. We are converting like 000, then 0001, then 00011. That goes like 11111, which is the 0 to 15 in decimal. But here we use the multiply by 4 method. Why? Whatever value you write here, multiply it with 4. For example, if the value is 1010, which is 10 in decimal, you multiply 10 with 4 to get 40, meaning your header is 40 bytes. The maximum value is 15. So 15 into 4, 60 bytes. The minimum should be at least 20 bytes. So values 0, 1, 2, 3, 4 are invalid because they give less than 20 bytes. So the first valid value is 5 because 5 into 4 equal to 20. Okay, and our minimum header length is 20 bits. 5 into 4 is 20. Now the next field is type of service. This is an 8-bit field. Today we call it DSCP. Okay, differentiated service code point. In IPv6 this is called traffic class. If we have to define some priority for any packet, whether it is a routine packet or has to be sent immediately, the next 4 bit are DTRC: delay, throughput, reliability and cost. In today's time we use many applications like WhatsApp calling, which is voice over IP. For services where we want less delay, we keep the delay bit as 1. If we want higher throughput rate of transfer, we keep it throughput as 1. For reliability, if we want packet to reach without dropping, we keep it as 1. For cost, if we want minimum monetary cost, we use 1. The last bit is reserved for future use. This is DTRC: delay, throughput, reliability and cost. Later this was modified to DSCP, where bits 0 to 5, 6 bits are reserved for DSCP and the remaining 2 bits are for ECN, explicit congestion notification. If these 2 bits are 11, it denotes congestion notification. Without dropping the packet, it sends a notification to the sender to reduce speed due to congestion. Now next field is total length. This is a 16-bit field denoting 2 raised to power 16, okay, which is 65,535. This represents the total length of the datagram, okay, including both header and payload. Next field is identification, flag and fragment offsets. These 3 fields are very important as they are part of fragmentation. Let me explain fragmentation in detail now. Fragmentation in IPv4. Fragmentation is a very important topic in IPv4, especially for competitive exams where many numerical problems come from this topic. These 3 fields, identification, flags and fragment offset, work together for fragmentation. Okay, fragmentation we have discussed before in our previous lectures also, but here we will discuss it in detail. Okay, now first is identification. This is a 16-bit field that can have 2 raised to power 16 values. When we divide packets into small parts and send them through different paths, when these packets reach their destination through different routes, how do we know that they belong to the same original packet? For this we use the identification field. Now next field is flags. This is a 3-bit field. The most significant bit, MSB, is reserved and its value is fixed as 0. Okay, the next bit is do not fragment, DF, which can be set as 1 or 0. If you set DF as 0, it means fragmentation is allowed. If you set DF as 1, it means no fragmentation is allowed. The third bit is more fragments, means MF, which tells whether this is the first, middle or last packets. If it's the last packet, MF is 0, otherwise it's 1. Next field is fragment offset. This is a 13-bit field that basically tells how many bytes of data are ahead of the current fragment. We use a scale of 8 here, so we divide the actual byte value by 8. Now we are looking at examples, so you will get a clear structure of fragmentation in your mind. So let me solve a numerical example. A datagram of 3000 bytes contains 20 bytes of IP header and 2980 bytes of IP payload. It reaches a router and must be forwarded to a link with MTU of 500 bytes. How many fragments will be generated? Also write the MF, offset and total length values for all fragments. Now we will look this example. Let's find how many fragments will be formed. Okay, if we send 500 bytes to the link, 20 bytes will be header and 480 bytes will be data. Okay, we have 2980 bytes of data and each fragment can carry 480 bytes of data. 2980 divided by 480. Okay, so this will become 6.2, which means we need 7 fragments. For the first 6 fragments, each will have 480 bytes of data plus 20 bytes of header as we discussed. So total 500 bytes. Total length equal to 500 bytes for one packet. For the 7th fragment, remaining data 2980 minus 6 into 480, which will be 2980 minus 2880, which is equal to 100 bytes of data plus 20 bytes of header. So 7th packet will be 7th fragment will be 120 bytes in total length. Now MF values, fragments 1 to 6, we have 7 fragments. So for MF values, fragment 1 to 6 equals to MF equal to 1 because more fragments follow. For fragment 7, MF equal to 0 because it is a last fragment. For offset values, fragment 1 offset is equal to 0 because no data ahead of this fragment. Now for fragment 2, offset value is 480 divided by 8 equal to 60. We have to divide it with 8 because 480 bytes of payload is ahead of fragment 2 in fragment 1. In fragment 3, how many bytes of payload ahead of fragment 3? Now 960. So we will divide it by 8. So it will become 120. Now for fragment 4, what is offset value? 1440 divided by 8, which is equal to 180. So we will solve this by this method. And the last fragment 7, fragment 7's offset value will become 2880 divided by 8 equal to 360. So we have calculated each fragment's offset value also. So by this example, it is clear that what is fragmentation. Okay, now moving forward to other IPv4 fields. The next field is time to live, TTL. This is the 8-bit field, important because sometimes packet get stuck in loops due to routing table changes or improper router information. This may create congestion. So the TTL field has maximum value of 255. When a packet reaches each node, the TTL value is reduced by 1. As soon as it reaches 0, we drop that packet, meaning it got stuck in the loop. The next field is protocol. This is 8-bit field, indicates which protocol from the upper layer is being used, such as TCP, UDP, SCTP, ICMP, IGMP, etc. Now the next field is header checksum. This is a 16-bit field used for error detection. Okay, it is possible that the address written on the envelope may get changed during transmission. If the address changes, it will be delivered to the wrong place. So whatever node or router comes on the way should calculate the checksum of the header and match it with the checksum value written here. Some fields like TTL keep changing, so selective fields are used for checksum calculation. Now the next field is source IP and destination IP. These are the most important fields, each of 32 bits. This is the address used in IPv4. Next field is IPv4 options and padding. Now options and padding have a variable size 0 to 40 bytes. Okay, if the IPv4 header is 20 bytes, then options are 0 bytes. If the header is 60 bytes, then options are 40 bytes. Now the first thing is record route option. Let's say I have a source connected to destination through routers, okay, R1, R2 and R3. As the packet moves from source to our destination, the record route option records the IP address of all routers passes through. Since one IP address is 4 bytes and we have maximum 40 bytes for options, we can theoretically store 10 routers addresses. But considering we need some bits for activation, we can practically store about 9 routers addresses. Now the next thing is source routing. Here the source itself tells the path the packet should take. Okay, it's like defining beforehand that my packet will go through specific routers in a specific order. There are two types: strict source routing, where you define the complete path, and loose source routing, where you define only some intermediate points and the packet can choose its own path between those points. Okay, now next thing is padding. The header length should always be in multiple of 4. If your header size is not a multiple of 4, like 23 bytes, you add extra 0 bits to make it multiple of 4, like adding 1 to 23 bytes to make it 24 bytes. This is called padding. Now moving forward to very important topic, IPv6. Introduction to IPv6. First, why do we need IPv6 when we already have IPv4? IPv4 came in 1970 and become very famous. Okay, we are still using IPv4 today. So what is the need of IPv6 here? The biggest reason is that IP addresses in IPv4 were 32 bits in size. Okay, meaning 2 power 32 possible IP addresses, which is approximately 4.3 billion addresses. This was sufficient for a certain time, but today we have the scenario of IoT, Internet of Things. We want IP addresses not only for mobiles and laptop but also for home appliances like AC, fridge, microwave, etc. Okay, we want to connect them through IoT and control them from anywhere. Because of this, the number of required IP addresses suddenly increased. IPv4 had limited IP address, and even after using techniques like NAT, network address translation, and classless addressing, it fell short. That's why we use IPv6, which has 128-bit address, providing 2 power 128 possible addresses. This is 2 power 96 times more than IPv4, a huge value sufficient for the next 50 to 60 years. Now we will discuss IPv6 header structure. Okay, the IPv6 header is much simpler compared to IPv4. The IPv4 header is a fixed 40 bytes, meaning 320 bits address. The first field is version. This is a 4-bit field. Okay, just like IPv4. Its value is 0110 in binary, which means 6 in decimal. Now the next field is traffic class, priority. We will call it priority. This is 8 bits. Okay, similar to the type of service field in IPv4. It is used for congestion control and priority setting. It contains differentiated service and ECN values for deciding packets priority. Next field is flow label. This is 20 bits field. It is used for real time data processing. Since IPv6 is also a datagram service like IPv4, packets go through different paths, but for real time application that need minimal delay and loss, we use flow label to convert datagram service into something like virtual circuit service. Next field is payload length. Okay, this is 16 bytes, similar to total length in IPv4, can represent up to 65,535 bytes. But IPv6 has an extra option called jumbograms, where you can send packets up to 4 GB, okay, using extension headers like hop by hop options. Now next field is next header. This field contains information about extension headers. IPv6 has a base header of 40 bytes. It is mandatory, plus optional extension headers. The next header field tells what type of extension header follows. Okay, your actual data comes after all extension headers. Now next field is hop limit. This is similar to TTL field in IPv4. It defines how many hops a packet can travel. The value decrements by 1 at each intermediate node. Okay, when it reaches 0, the packet is dropped to prevent infinite loop. The next field is source address and destination address. Each is 128 bit, okay, providing the huge address space that IPv6 is known for. Now we will discuss IPv6 extension headers. Okay, IPv6 uses extension headers for additional functionality. First is routing header. Its decimal value is 43, used when the sender wants to decide which router the packet should go through. It's like deciding the complete path for your packet. The second is hop by hop option. Okay, its decimal value is 0, used when you want to provide information to all hops in the path. Next is fragmentation header. Its decimal value is 44, used for fragmentation, but with a difference. In IPv6, intermediate routers cannot fragment packets. Only the source can fragment before sending. The next is authentication header. Decimal value is 51, used for authentication and maintaining data integrity using hash values. Next is destination options, which is 60 in decimals, contains information that only the destination should read. Okay, intermediate nodes cannot open this header. Next is encapsulating security payload. This is 50 in decimal. Okay, this is new in IPv6, used for security through encryption and decryption. So I have mentioned all the decimal value. We will convert it into binary and we will place it in next header field. Okay, now we will discuss advantages of IPv6. What is the first advantage? Larger address space. The primary advantage is the huge address space, 2 power 128 addresses, compared to IPv4 is 2 power 32 addresses. Okay, real-time data transmission. The next advantage is real-time data transmission. IPv4 supports real-time data transmission better than IPv4. Okay, important for live streaming, okay, video calls or extract. Now the next advantage is authentication. IPv4 has built-in support for message authentication, ensuring messages are from legitimate sources. Next advantage is encryption. IPv6 can encrypt message at the network layer itself, providing better security. IPv6 is also called IPNG, IP next generation, okay, because it's designed to work for the next 50 or 60 years without needing another version. With the growth of IoT devices, smart homes, and increased internet connectivity, IPv6 provides the scalability and feature needed for future networking requirements. That was the whole concept of IPv6 and IPv4. So that was very important concept, and that's it for this video. We will meet in next video. Until then, bye bye.